Okay, what next? Skip to page 6. Yeah, skip to page 6. Just moving right along now. Let's do one on page 6, and I'll leave the rest for you later. Let's see, do we have space to squeeze this in? Sure we do. 25 is another problem in this sort of same category. Dx over x squared minus 4x plus 7. What can we do here? Very unclear. If I try to let just u be the denominator, then I just don't have the 2x minus 4 in the numerator, so it's just not going to go anywhere. So what can I do? I can complete the square in the denominator. So this becomes dx over x squared minus 4x plus 4 plus 3. Chop, chop. So that's really like dx over x minus 2 squared plus 3. And now I'm starting to, the shape of this thing is starting to become apparent to me. This is going to be an arctan situation. Okay, you don't have to do this, but I like to let u be x minus 2, then du is just dx. So I can just sub that out of there really quick. Leaving me with du over u squared plus 3. Okay, and at this point now we've done this. This is now like our 4th time doing a problem like this. But here, since 3 is not a perfect square, it's just going to get a little bit ugly. So don't be scared when it gets a little bit ugly. Because, what do I mean by that? Well, in the denominator, I will factor out a 3, leaving me with u squared over 3 plus 1. Remember, making that a 1 was the whole point, because that's the derivative of arctan. So, well, okay, that becomes then 1/3 du over, but when I go to rewrite u squared over 3 in preparation to do a u sub, I have to kind of, it's a little gross, right? I have to let u be, like, I have to do like u over root 3 squared plus 1. To force it into the variable squared plus 1 format, which is after all what I want, because that's arctan, then I just have to do this. And so now my substitution of w equals u over root 3 is making me a little bit unhappy, but okay, we're almost done now. dw is therefore 1 over root 3 du. That's why I need to stick in a 1 over root 3 in the numerator, and to balance that out, a root 3 on the outside. So all of that becomes root 3 over 3 antiderivative. Du over root 3 is dw, and the bottom now is w squared plus 1. And now I can confidently apply the rule for that, which is that's arctan. So my final answer is root 3 over 3 arctan w. But w is really u over root 3, and u is really x minus 2. So it's x minus 2 over root 3 plus c. Okay. Good. Good. Alright. This video is moving right along. We're going to do most of the problems now from the next page. So let's go. Page 7. Oh man. Baby's just screaming along. Okay, 27. This is another classic kind of thing that, okay, this just comes up a lot, and so I swear that this is sort of objectively important. Well, important on some level, and yet it's hard. So think about this for a second. Yeah. Good. What?
The door is open.
Oh, the door is open this whole time. That's one reason why the baby's awake, maybe. Oops. Well, it's only open a little bit. Good video. Antidiff.
What the hell is wrong with you? You
Woo!
were screaming with the
Father
door
of the
open.
year, doing calculus, baby sleeping 15 feet away with the door open. Slightly ajar only. Hold on, just 1 second. I'm gonna go hold it for a minute. Okay.
What the hell is wrong with you?
Sorry, Theo. Okay, so, good, extremely professional here. We are trying to antidifferentiate side squared. How are we going to do this? Oh, well. Casual methods are just like not going to work. If you try to let u be sine, well, that seems promising, but then the derivative of sine is cosine, and there's just no cosine to be found. Another popular idea is to maybe think to write this as 1 minus cosine squared. And that might seem like a good idea at first, but then I don't know how to antidifferentiate cosine squared either. So I'm just stuck and I'm just going round and round in a loop. So I have to do something more crafty. Well, that's why we have a lot of trig identities, not just one or two. And one of the most important trig identities, and I've tried to review this many times this year, but I bet some of you are still like, yeah, I don't care about that one. Time to care about it. There is a trig identity for sine squared. It's called a power reducing formula, and the way you do this is you do it based on cosine 2x. So some sort of remedial pre-comp now. What is cosine 2x? Cosine 2x is cosine squared x minus sine squared x. I won't go back into why that's true. I will just assume you have that like memorized or something. Well, yeah, I won't explain why that's true. So this can be rewritten in two different ways. If I substitute for if I substitute 1 minus sine squared for cosine squared, then this becomes 1 minus 2 sine squared x. And so one important formula for cosine 2x is this one. I assume somewhere between 80 and 100% of you know this all very well. Okay, what is another option? Another option is that you replace sine squared with 1 minus cosine squared. So that's how you get cosine squared x minus, sine squared is 1 minus cosine squared, and then that becomes, when you distribute the negative, 2 cosine squared x minus 1. And so you have this other very useful formula for cosine 2x. Once again, I think everyone knows this, hopefully. Okay, well, so what? I'll tell you so what. This means I can now solve for sine squared. I'm running out of space, so I'll do the sort of algebra in my head. If you add that over to both sides and subtract that one, then maybe I can squeeze it in. So 2 sine squared x, is 1 minus cosine 2x. And so the real thing that the real takeaway here is that sine squared can be written as 1 minus cosine 2x over 2. Putting a box around that there. This is called a power reducing formula because it re-expresses the power of sine, specifically sine squared, in terms of trigonometric functions which are down like a degree, so to speak. And okay, what this says, in fact, is that sine squared is itself just a sinusoid. I don't know why I'm getting all into this. I swear we've had this whole conversation already this year a couple times, but now we're having it again. So sine squared, what does it look like? Well, you can kind of think of it as being like sine, but then, like squared. So when you plug in 0, you get 0. When you plug in pi, you get 0. When you plug in 2 pi, you get 0. When you plug in pi over 2, you get 1. But when you plug in 3 pi over 2, you're also going to get 1. And so it's kind of like, you know, it's sort of like sine, but a little bit more curvy or whatever. And then it's just going to repeat that again because it's always being squared, so everything's always positive. And in fact, what we see is it's just a cosine 2x curve smushed by a factor of 2, flipped upside down, and moved up a half. Okay, put a little star next to this. This is a little bit messy over here. While we're at it, we should mention that there is, of course, a cosine squared formula as well. What's cosine squared? Well, by doing algebra 1 on this, you get that it's cosine 2x plus 1 over 2. And now putting a box around this, and also a star. Those are the two power reducing formulas. This is something you did last year in Pre-Calc B. Things you can rederive on the spot if you forget them. They were used to derive the half angle formulas. You get the half angle formulas by taking the square root of both sides, and then plugging in, like, you know, x over 2 for x, basically. Okay, back to our problem. Well, we now see this is going to be great. This is going to solve all of our problems because what is the antiderivative of sine squared? Well, it's just 1 minus cosine 2x over 2. And while that looks a lot uglier, we have to admit that it's going to just be easier, right? Because this is like antiderivative. This is, well, yeah. This is just 1/2 dx minus 1/2 cosine 2x. And this is just, well, one thing has an antiderivative of 1, just 1/2 x, right? When you differentiate 1/2 x, you just get 1/2. And then what do we do over here? Well, here, okay, and now I will confess to, you know, even I, you know, will sometimes do this, right? Just like stick in the 2, undo the damage with an additional 1/2. And I won't actually, well, I might as well just be me and just say what we're doing here is we're letting u be 2x, and so du is 2 dx, and so that 2 and that dx are the du, and so this really just is 1/4 cosine u du. Therefore, the answer to this problem is 1/2 x minus 1/4. And the antiderivative of cosine is sine, so sine 2x. Boom, 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 boom. Sha. Okay. Good. 2 more to go. Let's do 28. 28 this is just not fun. But if I'm assigning this problem, I might as well suffer right along with you. And okay, this is not the last time in your life you're going to do this problem. I'm going to be but the last time in my class. What is cosine to the 4th x? Well, there is only one way to do this by hand, and the way to do it is using the power reducing formulas. So I'll assume you're, like, you know, taking notes at home and stuff and wrote all that stuff down. Ha ha ha. The only thing to do is to think of this as cosine squared x squared. And then apply the power reducing formula. And what is the power reducing formula for cosine squared? Well, I guess I know it. It's just 1 plus cosine 2x over 2, quantity squared. Is that true? It just totally is. Sorry, I'm just doubting myself for a second for some reason. Yeah, because cosine 2x is 2 cosine squared x minus 1, so yeah, okay. Whew! Now what? Well, now this terribleness is there's only one thing to do, which is to square that. And if I square that, I get, what's the best way to do this? Well, okay, I get 1 plus 2 cosine 2x plus cosine squared 2x all over 4 dx. That's just true. And now, this whole thing can be rewritten as, well, let's see. At the moment, I'll just keep it all together. So 1/4 plus 1/2 cosine 2x plus 1/4 cosine squared 2x dx. Alright, but now I do the only thing I can do, which is reduce the power yet again. So if cosine squared x is 1 plus cosine 2x over 2, then what's cosine squared 2x? Well, it's 1 plus cosine 4x over 2. Okay, so then this is 1/4 plus 1/2 cosine 2x plus 1/4 times, and in place of this cosine squared 2x, I have 1 plus cosine 4x all over 2. And that nightmare, now this is not really a nightmare, but it's not fun, needs to be simplified more. What can I do? Well, I guess that's like an eighth. Yeah. So that's 1/8. If I distribute this 1/4, and break this up, I get 1/8 plus a fourth, so it's 3/8. So okay, so this becomes 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x dx. It's not so terrible, but it's not exactly my favorite thing to do in the whole world. Now, these each can be antidifferentiated. And okay, I'm gonna do it the like fast way this time, where I just sort of cheat a little bit and just be smart in my head. I'm gonna stick that 1/2 here, and then okay, what's the antiderivative of cosine 2x? Well, it's got to be 1/2 sine 2x, because only then when I differentiate this do I get cosine 2x back inside 2 cancels the 1/2. And then here I get 1/8, and the antiderivative of cosine 4x is 1/4 sine 4x, because the derivative of sine 4x is cosine 4x back inside 4, which kills that. Oh no, I did it. I did the problem. Okay, and so believe it or not, the final answer to this problem is 3/8 x plus 1/4 sine 2x plus 1 over 32 sine 4x plus e. Okay, good. Oh yeah. Times it, perfect. Alright, we're gonna do one more problem, only, well, let me see what I'm gonna do. Let me erase this first. Okay, this problem, number 29. Alright, this is very controversial problem. What is the antiderivative of secant? This came up kind of obliquely a little bit in last week's, well, it didn't really come up, but it kind of came up. And in a Zoom call last week, someone just straight up out of the blue asked me how to do this, and no one was asking any other questions, so I went on a little side conversation about this. There are two ways to do this. There's the cheap way, and then there's the complicated way that's long and interesting to only some people. The cheap way to do this is to essentially just memorize this algebra trigonometry trick, which arrives completely unmotivated. And that is, if you multiply by secant x plus tan x over secant x plus tan x. A totally non-obvious thing to do. Then, when you multiply through on the top, you get secant squared x plus secant x tan x all over, on the bottom, secant x plus tan x. But now, suddenly, all our problems have been solved. Because I recognize secant squared iconically as the derivative of tan, and I recognize secant tan as the derivative of secant. And so if secant squared is the derivative of tan, and secant tan is the derivative of secant, then in fact that entire numerator is just the derivative of the denominator. Thus, if I let u be secant x plus tan x, then differentiating du dx is exactly this, right? Secant squared plus secant tan. Thus, okay, secant x tan x dx. And thus, I can just solve this entire problem by letting the bottom be u, and this just becomes du over u. And the answer to this, therefore, is ln absolute value of u plus c. And so what we get is ln absolute value secant x plus tan x plus c. That leaves me kind of unsatisfied, because how would I have come up with this idea of my own? And it feels like sort of a cheap in a way. I don't want you to think that calculus is just a bunch of cheap tricks. There is a more noble way to do this problem, but it is long, and so I won't do it right now. But ask someone on last week's Zoom call if you want to see an alternative solution. Okay, I said I was going to stop there. There is a page 8 for the 90% of you who have this packet in your hand because I printed it. I don't want to get bogged down in these kind of problems this year because I think they're sort of hard. But I'm maybe just going to do one problem from the back, and which is page 8. So I don't know, like turn off this thing right now if you don't want to. Let's see, what's the hardest one? Maybe I'll just do the first one, actually, because it's not the hardest, but it gets the general idea. So I made this whole packet, and I made this page called Miscellaneous Substitution. And this very first problem is, so I guess it's number, oh boy. Sorry, I didn't print this. 1 second. It's number 31. 1 over 1 plus root 3x dx. Okay, so you could turn this off right now, or you could watch for 5 more minutes. I'm going to do this problem. Then I'm going to turn off this camera, leave you to finish the rest of this packet. You don't have to do page 8, so just pages 2 through 7, and I will make a video doing all the problems that I didn't do just now. How do I do this problem? You might be wondering. This problem is really hard because honestly, there is no obvious thing to do. It doesn't look like some chain rule happened here. I don't see any substitutions which particularly seem helpful. And so what makes these problems hard is because you're just blindly trying some crap and hoping that it works. In particular, my vast experience with problems like this suggests that if I let the entire bottom be u, good things are going to happen. Okay, and everyone should be able to handle these problems. Once I tell you what u is, you should be able to sort of do these problems. The hard part is figuring out what to let u be. But if you just kind of trust me that this choice of u works. What is the motivation for this? I guess the only real motivation, which I mentioned last week, is that I like my denominator to be a single term. If my denominator is a single term, then that supports splitting. Okay, let's see what are the ramifications of this. Well, if u is 1 plus root 3x, the next thing we used to do is to differentiate. So what is du dx? Well, I can differentiate this right-hand side. Derivative of 1 is 0. This is going to be 1/2 3x to the negative 1/2 back inside 2. Sorry, back inside 3, I mean. Okay, and so what is du? du is 3 over 2 root 3x dx. Yeah. 3 over 2 root 3x. Okay, this is correct. I simply differentiated, that's all, not a big mystery. But now I'm just very confused because I don't have this in there. And okay, at this point though, I just don't despair. Instead, I just solve for dx. Because I ultimately would like to perform a rewriting of this antiderivative in terms of u's. So okay, one step already is done, right? The bottom is just u now. So just to figure out, if I can just figure out what dx is, I'm done. So in other words, I need to write dx in terms of u's. So okay, so, well, what do I get? I get that du times 2 root 3x over 3 is dx. So I got this line just by doing algebra 1 on the previous line. Alright, but now I'm sort of very confused because, well, okay, I'm not that confused, but okay. So here I have my 1, maybe I'll do it like this. And then what is dx? Well, it's 2/3 root 3x du. But in some sense, if my goal is to convert this antiderivative into one involving u's instead of x's, then I'm sort of not done yet, right? Because I still have a mixture of x's and u's here. Well, I go back to this u and I see that in fact root 3x is just u minus 1. So now doing algebra on this first line, I get that root 3x is u minus 1, and thus I can complete this whole process here, because what I get is 2/3 antiderivative. I just replace a root 3x with u minus 1. And sort of like magic, I have converted this problem into one involving just u's, and now this looks very doable. Let's go. This is 2/3 1 minus 1 over u du. In other words, 2/3, oh, and now I just can do this, I guess, right? 2/3 times u minus ln absolute value u plus c. Okay, and what is u? It's that whole mess. So what I get is like 2/3 times 1 plus root 3x minus ln absolute value of 1 plus root 3x, and I guess I don't actually even need the absolute values because it's all positive. Okay, I have one more sort of small thing to say. This is totally correct. This is totally correct. I'm just checking my. Oh no! Oops! I did make a mistake here in distributing the 2/3. But other than that, it was totally correct. The last thing I'll say is that if you probably like type this online or something, you won't get this. What you'll get is what computer engines will do is they'll distribute this 2/3, and they'll sort of get 2/3 root 3x minus 2/3 ln 1 plus root 3x. But then notice that there's just extra 2/3 here, but the c is just c, so they'll just do that. If that makes any sense. Constants can be blown off. So either of those two answers is totally fine. Okay, you don't have to do any other problems on this page. I'm done teaching you. This was sort of phase 2, and then you're going to finish the rest of this packet on your own. Goodbye.